Let's see what we got. Okay, Big Bang. Can you kind of just generally say what a Big Bang was? I like what the video talked about, kind of that little white, small, tiny thing, smaller than an atom, basically had all of the matter and the energy of our universe. Okay, so actually they call that singularity, kind of like a black hole singularity. That's the term I've heard it called. So our universe cooled over time. I think they did a good job of kind of showing that. Oh no, come back. There we go. Oops. There. Where's my figure? There it is. There's the figure I was after. Okay, so I've got a couple of charts kind of like this, but they're both a little bit different. So the way this works is, notice we have time along the x-axis, okay? So if I say BB, hopefully you guys know that's Big Bang, okay? And then just a fraction of a second, okay? This actually is a base 10 scale. So this is 1 times 10 to the 45th seconds, okay? So over here, this is 1 times 10 to the negative 5th seconds, so that's 0.00001 seconds right there, okay? This right here is 10 to the 5th seconds, so that's what, 100,000 seconds, okay, right there. Okay, this right here is 10 to the 15th seconds, okay? So that seems like a big number, so you put 1 comma with 15 zeros. So in case you're kind of wondering how that works, we are about 4 times 10 to the 17th seconds after the Big Bang. I don't use the Planck time thing, okay, but, okay, so that's kind of where we are. So along the y-axis, we have temperature. So, of course, I like the video because it said how very hot it was, okay, and it's been cooling down ever since, okay. So 10 to the 32nd Kelvin units, that's like how hot it was. That's pretty hot, singularity. Okay, and right now we've cooled down to, you know, down here. Now this is our universe temperature. Yeah, your universe temperature. So we definitely have this cooling thing going. Okay, I like what the gal said. Actually, I'm going to put this whole slide up here. All of this stuff was stuff we saw in the video. Okay, this is the whole matter, antimatter stuff. Wait. This one, down here. This is the matter, antimatter stuff right here, okay? Was that not cool? That basically when energy was converted into matter, you got equal matter and antimatter, but just a little bit extra matter, and that's how we're made of, matter, okay? And the one above it is taking energy and converting it to matter. This over here, to me, this is not any small thing. This is CERN. You've heard about the particle collider. There's more than just one, but this is probably the most famous one. The God's particle, the Higgs boson, this is where it was found. You can kind of see those white lines here, okay? Kind of they go out and around, okay? That actually, as I understand it, I think they kind of showed it, they basically start 2 particles and they send them in opposite kind of tubes, and I think they probably cross each other, and then they get going fast and faster, and then they open up the channel for them to collide in that detector that was like 5 stories high. Okay, and that was where they were creating the conditions that were similar to the time of the Big Bang. That is so cool. HLC stands for Large Hadron Collider. Okay, so at the end of the video, he said basically all of the forces of physics were created at the time of the Big Bang. There are 4 forces that were created, or yeah, they were ultimately created from the Big Bang. And they're here with us today, but they weren't all separated like they are today. I know it's kind of weird, but if you read through each of these, we're familiar with gravity. Electromagnetism is kind of like... it's what holds our matter together. It's like protons and electrons being attracted to each other. The strong and the weak force kind of go together. Those are like things that happen within the atom, okay? So we have those 4 forces that are with us today, and they had to have been birthed at the time of the Big Bang, but not individually. So at higher temperatures, remember it started out really, really hot. At higher temperatures, some of those forces come together. So for instance, there's this electroweak force, which combines the weak force of the nucleus with the electromagnetic force. Okay. There's the gut force, which actually has 3 forces come together. This is even hotter. So the 3 forces, if you want to think of it this way, it's all 3 except for gravity. So what does that mean? It means if we take out gravity, the gut force is the electromagnetic, strong and weak. Okay? Then, and actually those are more obvious than this last one, there actually seems to be probably some sort of super force at the very, very time of the Big Bang under those hot, very terribly hot temperatures, where the gut force and gravity were actually connected. So now here's another table. Okay, now the video didn't talk about this, but just let me kind of talk you through it. This one is, let's see, this one's backwards. So actually, from the one we looked at. So this one goes like this. Time goes this way. Okay, so this is still not here today, okay, but today would be clear over here. Day would be clear over here. We got time going that way. And so, like I said, early on, probably all 4 forces were together. Then it breaks out into the gut and the gravity, and then the gut breaks out into electroweak and strong, and then electroweak breaks out into electromagnetic and weak. As it what? Cools. So down here we have, can you see the cooling? Cooling. Time and cooling. I don't know why they did these both backwards, but they are. 10 to the 15th Kelvin, by the way, that's still pretty darn hot. But about that time, we go ahead and get the 4 forces broken out, or somewhere in there, that we know and love today. All right. So you might recognize some of these eras in the video that we just watched. But the early eras are defined by the forces, and the later eras are defined by the particles. So for instance, it kind of goes like this. They talked about Planck time. So Planck era, as I understand, is probably where there's the most uncertainty as to, well, what was happening there? So all forces were unified, okay? Then we have the gut era, and like it's defined by the force. So what is the gut era? Basically, it's a time where you get gravity breaking away from the other 3. And notice that I've got kind of some bars up here with regard to time, how long it took, and the approximate temperature. And then the electroweak, and the electroweak was basically the gut broke out into 2 forces. I don't have a whole lot to say. These later ones were defined by particles. To me, this is where it gets just a little more interesting. So the particle era has to be where the energy was being converted. It's getting cooler, and energy is converted into matter. Okay. So this is where it says matter and antimatter. Okay. It's just still very chaotic, relatively dense. Remember with the cooling, we have expansion and cooling at the same time. This is still not atoms. This is I think, to me, I would probably call these quarks. I don't have it in my notes, but quarks are just like subatomic particles. There's different flavors of quarks and that sort of thing. Okay. It continues to cool down, and then we have the era of nucleosynthesis. Synthesis means to put together. Nucleus, nucleus, maybe you kind of see that. Okay. And here's where we see nuclei beginning to fuse. The video talked about the formation of hydrogen. Remember, the symbol for hydrogen is H, so we have our hydrogen nuclei. Okay, era of nucleosynthesis. Then we have the era of nuclei. Now, the era of nuclei, and I kind of, on your unit exam, pulled out some random facts about this whole eras. One of the random facts I think I pulled out was, how long did the era of nuclei last? 5 minutes is what you're looking for. Okay. All right. Then after nuclei, we have something that can exist at cooler temperatures, which would be the atoms. Now remember the video, the guy, they said it in different ways, but basically kind of the 380,000 years after the Big Bang, something happened. And what happened was basically those electrons settled down to go ahead and become associated with nuclei. The electrons stopped creating that milky haze that we couldn't see through. Okay. The background radiation that we're going to spend a few slides talking about, the Penzias and Wilson sort of thing with the pigeon crap, okay? That's actually, then they were able to see the information, the energy that was released at that time. So 380,000 years after the Big Bang. And I don't have a little thing to go along with this, but we're currently in the era of galaxies. Okay, makes sense? We got our quarks, we got our nuclei, we got our atoms, and now we're into normal matter. We're into galaxies. Okay, so just a little bit about the whole, that background, what we call background radiation. Sometimes I'll use the word microwave background radiation. It's abbreviated, cosmic microwave background radiation, or CMB, okay? Like I said, it happened after the era of atoms, where basically those electrons kind of settle down around nuclei. And I like this. This is one of my favorite little drawings down here. Basically, can you kind of see the chaos here? If you look real closely, you'll see free electrons kind of hazing up the joint. Over here, those electrons have settled down and are associated with nuclei. So then energy can flow. All right. So, oh yeah, let's see, where is it? All right. So recently we talked about, and actually it's on your test in one form or another. Do you remember the cosmological redshift? Where basically I showed a picture of a balloon kind of expanding and a wave on the balloon, and as the balloon expanded, the wavelength got longer, okay? So that's the expansion of the fabric of space and time is how I think of it. So kind of along those lines, this energy that was released so long ago had a particular temperature, okay? Relatively hot temperature, relatively warm. But the cosmological redshift has basically taken that red hot temperature. What is hot? What is heat? That's infrared, okay? Remember when we talk about our cousins, okay? Let's see. Here we have IR. We have visible. Okay, let's see. After IR, we have microwaves. And then we have radio waves. Okay, so this is longer over here. So basically, the cosmological redshift is taken something that a heat and stretched it out into longer wavelength. And we can actually tell what that wavelength would be. I can't, but they can, the physicists. All right. So I was glad that we watched that video, because one of the pictures I pulled is a picture of their Penzias and Wilson's Gizmo, their radio telescope, okay, where they were actually trying to eliminate that kind of static signal they got at a particular frequency, which just happens to be the hiss of the Big Bang. Okay. But anyway, just like the video said, and the video didn't say this, but actually they earned a Nobel laureate prize in astrophysics for their work. Okay, so they ended up sending up a couple of probes. Okay, first this probe kind of gave them a blurry image. Okay, and then a later probe. Actually, there's 3 probes. I think they only mentioned 2. But this actually is where they describe kind of the cool and the warm regions, of a long, far away. You think Star Wars is long, far away, okay? Of the distant universe. So it's kind of like the theme of what we've been talking about this semester. If it's cool, basically gravity can go ahead and do its thing. Okay, if it's hot, forget it. So cool regions actually have a fighting chance of forming galaxies and stars within the galaxies. Heaven forbid, planets around the stars. Okay, so that's actually kind of what that looks like. Okay. So there are actually two things that support this overall kind of what these eras and everything we've collectively call the Big Bang. And one of them is this, the abundance of hydrogen and helium in the universe. Okay. Actually, it's basically a 3-to-1 or 75% to 25% sort of ratio. And I'll just kind of leave it to yourself. I convinced myself by reading this slide, oh, that's how that works. But basically, the fact that we have the relative amount of helium that we have, which is about a quarter of the amount of hydrogen we have, it's all goes back to the eras that we were talking about. What else we got? All right. Do you remember when the guy said that basically the universe expanded faster than the speed of light? And even school children know that you can't go faster than the speed of light. But I kind of go track with him on this because he basically said the fabric of space and time was expanding into nothingness. So the problem with the cosmic speed limit of the speed of light is the fabric of space and time kind of gets in the way. And this was the fabric of space and time expanding. So anyway, I think he even said, one of them even said something about these little cosmic ripples. Okay. This, by the way, is called inflation. I wish the guy right then in the video would have called it inflation, because this is what it is. Okay? Inflation is when it just went from the size, I think he said, of a, out to the size of a baseball.
From an atom to a baseball.
Atom to baseball, thank you. Okay, faster than the speed of light. But these little, to me, these little perturbations, these little kind of unevennesses that actually occurred at the time of inflation, those ended up being kind of the same kind of perturbations that we see on the cosmic microwave background signal. Those are our cool and our warm regions, okay? And without kind of our cool and our warm regions, then we would have been in trouble. That's to say, we wouldn't have had gravity to kick in and go ahead and create the galaxies and the stars and the planets. Okay. All right. So inflation. Inflation also helps explain this over here. Don't worry too much about the shape of our universe. But inflation also helps to explain the fact that we actually, these days, we actually see parts of the sky, region A and region B, which looks like they were once basically together, okay? And so with inflation, that makes sense. Basically, there was this inflation to this point, and then they've been, because of the universe expanding, they've been getting farther apart all the time, okay? Yes, don't worry about the flat thing. All right, is this the last slide? All right. So the last thing is something called Olber's paradox, and I'll put this whole thing up here. Now, they did not talk about Olber's paradox. And I'm going to try to see if I can find a short little video in Minute Physics to talk about this. So Olber's paradox basically starts, if you've ever done any thought, in math you do these theorems and axioms and you come up with, you kind of logically approach something like this. So it starts like this. It's like, all right, why when we go outside tonight is it going to be black skies? Okay. So this says the entire nighttime sky would be filled with stars. Okay. So for instance, it should be if the universe was infinite, think about this, if there were no initial beginning, which we call the Big Bang, if the universe has been chugging away, okay, that means, and forget the 14 billion years old, that means if it's like 1,000 billion years old, longer than that. Stars have lived their lives, they've been shining light, that light has been in transit to us for forever. So basically we have light coming from everywhere. Okay? Even as we turned away from the sun, that part of the sky would just have all sorts of miscellaneous light because there's a star everywhere you look that is sending light in all directions, including ours. Okay. So, according to this night time would be filled with stars if the universe was infinite and if it wasn't if it was unchanging. Okay. So we don't see stars everywhere. Okay. So since we don't see stars everywhere when we turn away from the sun in night, okay, either the universe has a specific limited amount of stars, and or the universe has been changing over time. Okay. So actually, what we now understand as the unfolding of our universe actually says both of these, that the universe has a finite number of stars and the universe has been changing over time. Okay. So why don't we see light in all directions? Because we've talked about our cosmic horizon, where basically we can only see, actually now we know it's the Big Bang plus 380,000 years after that, right? But we could only see so far because before that, our universe didn't exist. Well, now let's go ahead and take a break.